I'll just go ahead and share my screen now, and I guess I'll get started maybe a minute after 1, just to give people a chance to come on in. Hopefully my watch is synced up enough with my computer time, but I think that'll be okay. All right, looks like we do have folks starting to trickle in. That's good. All right, one more test. Can folks see my slides?
Looks good.
All right. Okay, well, for the sake of time, I think I'm going to go ahead and start explaining the session. Thanks to everyone for coming to the TESS FFI light curve splinter session. So I'm hoping this can be a good sort of introduction to the different full frame image light curve tools that are out there. I know that there are a lot of folks who have sort of been working on really hard on developing these pipelines, and we haven't had the chance to sort of compare or contrast them too much, or figure out what are the best science cases that we're all trying to use them for, or that they should be used for. And so hopefully we can address some of those questions in this winter session. So the way I want to do this is basically break everything into 2 components. So the first part will be sort of run more as a typical kind of intro, typical webinar, like we've had most of these other sessions at this meeting. So basically, we'll be starting out with 4 kind of large pipeline introductions. So starting with the quick look pipeline, followed by the Eleanor pipeline, then the TASOC pipeline, and the SPOC pipeline. These will be sort of traditional 6 + 2 minute presentations. I'll be monitoring the Slack to see if people have questions for the speakers, and trying to keep us all to time and everything like that. And then actually after that session, after those 4 presentations, which will be recorded, we'll then be turning off the recording so that other folks can sort of introduce their own FFI tools. I know a lot of people have developed those as well. And so if you're interested in giving kind of a 1-minute presentation on your FFI pipeline tool, please post it to the FFI Pipelines channel on Slack with like a 1-sentence description, and I'll try and sort of moderate that. We'll try and accommodate 5 to 8 presentations, depending on how much time we have, maybe even a couple more, and see if we can, give everyone a chance to sort of talk about what they've been working on with the TESS full frame images. And then for the second half of this session, that'll be run more like a workshop. So there, essentially, I want to encourage folks to use either the Slack channel or direct messages, or use GatherTown to sort of form groups and potentially hack on whatever FFI light curve problems really interest you. So in GatherTown, for example, if you haven't already been to the space, they have a couple of breakout rooms where you can kind of literally just go into a separate room and talk with a smaller group of people. So if you'd like to do that, that seems like a good way to try and hack on these FFI pipelines and tools and things like that. And then at around, I guess, 2:15 or UT 21:15, I'm going to encourage folks to add a slide to the end of this Google slide deck. So I'll post a link to this in the Slack channel so that people can add their slides. And I've also added one example slide so that you guys have an idea of what to sort of talk about in that presentation. And then with the last 30 minutes of this session, we want to present those slides. And so the way that's going to work is I'll just share my screen so I can share all of those slides and sort of let folks unmute themselves. If you could pick one presenter from each group to sort of talk about your slide for roughly 1 to 2 minutes, depending on how many slides we have. And then we'll try and accommodate as many of the slides as possible so that we can see what people are excited about when it comes to dealing with the TESS full frame images. And yeah, I'm really excited to see what kind of science people are working on and how we can all collaborate to have the best results that we can from TESS. So, all right, I think that's pretty much all I had. Oh, just in case you didn't already know, here's the Slack link for this channel, as well as the GatherTown link. Unfortunately, you can't click on them, so I guess you'd have to type out all those letters, but they should be available on the Slack channel as well. Okay, so without further ado, I'm going to stop sharing my screen, and we'll hear from the first presenter, Michelle Kunimoto, about the Quick Look pipeline. So Michelle, go ahead and take it away.
Okay. Obligatory, does everybody see my screen? Is it coming through? Okay, great. So thanks, Sam. I'd like to begin by recognizing my fellow QLP team members listed here who all help keep QLP operating essentially 24/7 and contributing to tons of TESS science. So for those of you who are newer to TESS, QLP is MIT's pipeline focused on identifying new TESS objects of interest, or TOIs, from FFI observations. Our pipeline goes all the way from essentially the raw FFIs to triaged planet candidate reports. And our targets are all observed stars down to a limiting magnitude of 13.5, which comes out to about 1 million stars per sector. So I only have 6 minutes. I'm going to start by providing an extremely condensed version of the main steps of QLP. And if any of you have more specific questions, you can reach out to me on Slack. I'm also going to be on GatherTown at the TOI help desk, or you can check out Chelsea Huang's research note on QLP, which details light curve production for the TESS primary mission. So the first major process is light curve generation, which is done on a cadence of once every TESS orbit. We start by calibrating the FFIs and correct them for various instrumental effects. We remove a significant level of scattered light by subtracting a global background and perform a simple median subtraction. Then we perform a multi-aperture photometry, which is done by summing up all flux within circular apertures centered on each of our targets. We use 5 different sizes, ranging from 1.75 pixels in radius to 8 pixels in radius. And we also subtract a local background from all of those fluxes to remove smaller scale features. Convert this difference flux into an absolute flux based off of what we expect the flux of each star should be given its TESS magnitude. And an example of the resulting light curves are shown here with the smallest apertures at top and the larger apertures offset below for visibility. These light curves obviously have a lot of variability in them still that aren't going to be due to transiting exoplanets. So we detrend these using basis spline fits. We flag out poor quality data points based off of identifying them from our bright star light curves. And since we have 5 light curves available for every target, we assign the optimal aperture based off of the magnitude of the star. So the largest apertures will be the most appropriate for the brightest stars. Optimally, our machines are capable of producing a full orbit's worth of light curves for all 1 million stars in just a few days' time. Afterwards, we've got all of our orbit light curves and we stitch those together into a multi-sector light curve for every target. So in this example here, we're combining year 1 data with year 3 data, and that year 2 gap in the middle is just because TESS observed the other hemisphere. We perform Boxley squares transit search as implemented in VAR tools on these light curves. And of all the steps in QLP, this is the one that takes by far the longest, anywhere from maybe 1 to 2 weeks, depending on how many stars we're observing and how much overlap there is with previous sectors. And finally, we perform an automated and an internal manual triage to pick out the most promising signals. We make reports for all these candidates with really useful views such as phase diagrams, odd-even transit comparisons, significant secondaries, transit model fits, and also FFI difference images for identifying off-target signals. Once these reports are done, they are sent out for delivery, and group vetters discuss which signals should be alerted as new TOIs, which is typically a few hundred we sent out, and maybe a few dozen of those are new TOIs at the end of a sector. And usually by the time we're finished with this full sector processing, we're already ready to start processing the next orbitive data. So that's essentially a really condensed version of the QLP pipeline. In terms of what's publicly available, all of our primary mission light curves are available en masse as high-level science products, and I've included an example Python notebook for the later workshop session so that all of you can access those using either AstroQuery or Lightcurve. We also have all of our vetting reports available on the TESS Exoplanet Vetter website, although you do need an account to see those. But all of those are available for previous sectors as well. I do want to highlight some of the incredible science that our team has been doing recently with QLP outside of standard TOI identification. First is a project led by one of our developers and operators, Evan. He's also got a poster on this, so I encourage you to check that out if you haven't already. But he's performing the first systematic search of FFIs for multi-planet systems, and he's already found a few new candidates from older TOIs. His code has been incorporated into QLP starting in sector 33. So from now on, we are going to be sensitive to multi-planet systems in our regular processing. Secondly, is a project that I've been leading with my collaborator, Tansu Dalin, and this is searching for planets around fate stars with FFIs. So as I already mentioned, QLP goes down to a test magnitude of 13.5, but our vetting stage only goes down to 10.5 magnitude because of the sheer number of signals that we have to look at every month. So this is essentially what I was doing is looking at that range of magnitudes that we hadn't vetted before. I included an independent vetting pipeline to do this automatically, manually reviewed them, and as a result was able to release more than 1,600 TOIs over the past few months. And certainly there are many more to come. I'm improving this vetting pipeline and moving on to the extended mission. So on my last note, as I finish up here, I just want to outline some quick updates that are going to be coming for QLP. The first is when TESS observes the ecliptic, we're actually going to be combining our processes with the K2 light curves, courtesy of Andrew Vanderberg, in a combined K2 QLP analysis for transit searches. We're working on improving our detrending algorithm, which is going to work more similarly to SPOC's PDC algorithm and improve light curve precision. We're also hoping to implement a GPU-based BLS, which will see a 1,000 times speed up in our BLS runs and allow us to look at a much larger frequency grid. And finally, we hope to start releasing our current extended mission light curves as high-level science products available to the public in the very near future. Thank you.
Okay, fantastic. Thanks very much, Michelle. I have one quick question. Well, I have a couple of questions, but I'll start off with this one. So in that faint star search, it looked like almost all of your new targets that you found are hot Jupiters.
Yes.
Can you say a little bit why, why exactly you had such a strong, or why all of these targets are basically hot Jupiters, I guess?
Right. So when you look at these fainter targets, the light curve precision is not going to be as good as the bright targets. So you really need deep transit depths. So that either means planets around small stars like M dwarfs, or really large planets around bigger stars like G and F dwarf stars. So it turns out that at these magnitudes, they're really dominated by hot Jupiters because they're the easiest to find. Again, this is also based off of just the primary mission. So a lot of our light curves had only a single sector's worth of data at the time, and QLP is going to be most sensitive to orbital periods less than 10 days with those kinds of searches. So with the extended mission, I'm hoping that we'll be able to find longer orbital period planets as well as smaller planets. And we were able to find, I think it was a few dozen kind of level 1 candidates, which are those smaller than the size of Neptune. So we're still sensitive to these at these faint stars, but yeah, it's really just, it gets really hard to find good planet candidates and distinguish them from false positives at that magnitude.
Awesome. Well, thanks very much. That was great to hear about all the exciting science that's coming out of the QLP and will be continuing to come out of the QLP in the near future. All right, but for the sake of time, we should probably move on to the next talk. So that'll be from Adina Feinstein about the Eleanor pipeline. So Adina, go ahead and take it away.
Okay. Can you see this okay?
Yes, I can.
Sweet, thanks. Hi, everyone. Thanks to Sam for organizing the session. I feel like whenever in the past we've been at a conference talking about TESS or AAS, all of the people who have FFI pipelines are like, we should compare all of our light curves and see which ones are, best for what science. And like now I'm excited that we're finally doing that. So I am the lead developer of the Eleanor pipeline, and I want to acknowledge all of my co-authors who helped to develop this, as well as all of the people who have submitted GitHub pull requests over the past 2 years. And here I'm just going to give you a very brief overview of the steps that the software takes. So I feel like because this is the FFI session, we always have to start with these beautiful pictures of test years 1 and 2, where you can see basically everything in the FFIs from the Milky Way to the stars. You can't really see asteroids in this one, but trust me that they're there. And we really developed Eleanor in mind with the user. And so originally we had planned to release light curves to MAST. Now I think Eleanor is just going to be strictly a software tool for people to go in and get light curves for whatever science goals that they want. So really in the sense of this create your own adventure, like Splinter session, that's basically what Eleanor is now. It's a create your own adventure light curve for your science goals. And so these are just the overviews of the steps that are taken behind the scenes, and I will step through them individually, starting with the first one. So I think we're all very well aware at this point that there are large test background issues and large systematics going on. And so within Eleanor, we tried to address this with 3 different approaches. The first one is that we break the FFIs down into these postcards, which are 148 by 105 pixel regions. And the reason why we do this is because we think that we can get a better estimate of the background from these smaller localized regions rather than using the entire full frame image. And so what we do is we mask all of the bright stars with some sigma outlier, and then estimate a median background from that. And so just from this postcard, you can see this is the time and then the background flux. You can see that it really nicely catches those large ramp ups at orbits, as well as some of the like reflected Earthshine going down and those bumps that we would expect. So that's just one of the approaches we take. The other one that is only available right now through sectors 1 through 13 is we actually linearly interpolate across the background in the postcard to create a 2D model. And then what you would do is that for your target pixel file, you would subtract the background pixels directly from that. So rather than subtracting a constant, you would subtract this 2D frame. That's just the modeled background. The other thing that we do is very similar to, I think, what the Quick Look pipeline or SPOC pipelines do, which is we mask really bright pixels on the target pixel file level and then create a background flux from that as well. So very much so like the original bigger postcard one that we saw before, we still see these really large ramp ups. And I should say that these are 3 options that we have within Eleanor, and then it tests all of these along the way and then tries to create the best light curve. And here the Eleanor like corrected flux or best light curve is really optimized for exoplanet searches, but we provide all of these steps along the way so that you can go back, remove some background that might be in the way or kind of flattening out like any long-term rotation signals or whatever you're looking for, and then you can apply new backgrounds. And so, yeah, we store each of these in the FITS files, and they're indicated by a keyword header called BKG_level. So there's the 1D postcard level, there's the 2D postcard level, which is the 2D modeled background, and then there's the 1D TPF. The next thing that we do is select an aperture. And so very similar to the Quick Look pipeline, we have a library of apertures that we automatically test. These are them, they're 21 different shape sizes, also weighted and binary. So yellow here is 1 and purple is 0. So you can see some of them have different weights applied to them. The reason why we're choosing some of these L shapes are from lessons learned from Kepler and K2. And so we thought that they might be very well applied here, especially for stars in crowded regions. To save some time, we limit the apertures to the smallest apertures for targets that are fainter than a test magnitude of 13. And conversely, we limit them to the largest apertures for stars that are brighter than test magnitude of 8. We don't really handle oversaturated stars well. So for things that are test magnitude of maybe 5 or brighter, you would want to use some kind of extended aperture to catch those blend streaks, but we don't do anything like that behind the scenes right now.
And then also, even though we choose one aperture at the end, all of the light curves from each of these apertures are given to the user in the code. So if you don't like the one that we choose, you can always go into the library and see what the other light curves look like. The next thing that we do is create quality flags. So we actually use the quality flags from the 2-minute targets and bin them down to the 30-minute cadence and take whichever ones are applied to the entire full frame image. So here is just an example of a light curve that's colored by the quality flag here, yellow being bad quality, purple being good. And you can see that it really captures the ramp ups between the orbital breaks as well as the momentum dumps, as well as some of that jitter going on. So this is just an example from, I think, sector 3. So you can see that it catches some of those nice wigglies going on there that you don't want in your light curve. We also track the centroid motion just by calculating like the weighted mean of the pixel values and provide that to the users as well for them to do what they want with it. We also do detrending along the way. So although we provide the raw light curves, we also do detrending with these co-trending basis vectors that are provided for the 2-minute targets. And see, these are some examples of those. These are the first 3 co-trending basis vectors that are binned down to the 30-minute cadence. We originally binned them down because they weren't being provided at 30 minutes, but now I think they are. So those are just taken directly from the high-level science products that are provided. And you can see that some of these catch the really nice long-term trends from TESS as well as some of the other systematics going on. And so after we apply this detrending, we're trying to optimize our light curves for exoplanet searches. And so what we do is we measure the combined differential photometric precision, or CDPP, from each light curve. And what that does is it basically measures the standard deviation outside of a transit. So here, this is just an example of a light curve that I knew that had a transit. What we do is we do a sigma cut to try and remove anything that might or might not be there, and then measure the CDPP that way. So for this one, you would measure it for the yellow line. There are 4 light curves that we provide by default, or 3 by default. 1 is optional, and I'll step through them. There's the raw one that only has the background removed and no other processing. There's the corrected flux that is a combination of the co-trending basis vectors and regressing against the centroiding motion that we do, the background and time. We have the principal component analysis flux, which is only detrending with the co-trending basis vectors. And then also we have a point spread function modeling keyword that you can put in if you want to model your light curve, but we don't do that by default because it's not as computationally, it's more computationally expensive. And so at the time when we wanted to do this for millions of light curves, it wouldn't have made sense, but users can do that when they want. I think this is a pretty good overview chart of which kind of fluxes work well for which science. So things for transits and eclipses, you want to use your corrected, your PCA or your PSF flux. If you're looking for long-term trends, those get removed in the corrected flux, so you definitely don't want to use those. Short-term variability is pretty well captured in the raw flux and the corrected flux. And for solar system science or extragalactic science, we don't really do anything for that. So we would recommend the raw and then doing your own detrending along the way. So as I said at the beginning, this is really designed with the user in mind. You can design your own apertures, put those in if you want. You can apply your own custom detrending techniques. We also provide a suite of visualization tools to help, especially because the test pixels are so big. So we provide things like pixel by pixel light curves so you can pinpoint where exactly your signal is coming from. Adaptability, it works well with the FFIs of all different cadences. So I'm hoping that it doesn't break with the 200-second cadence FFIs, but I guess we'll see when those come. It's fully open source. It's hosted on GitHub, and we always accept pull requests. We have a bunch of tutorial notebooks online at the documentation, as well as some that are generated based on lessons learned that we've accumulated along the way. And it's very easy to integrate with other software. So we even have a function that says to light curve with a K, no space, and we'll bring you into that object. So you could do all your kind of science with that. And with that, I'll leave up all of the resource links and take any questions. And I'm sorry if that was over time.
No worries. Thanks very much, Adina. That was a great great overview of Eleanor and on all the different functionalities that it had. And it's really nice to see that table to give us an idea of where which sort of light curve is best for which science case. So since we are a little tight on time, I'm going to encourage you to go to the Slack channel to see if you have any questions there. I've also posted the Google Drive for this session. So if you want to look at those tutorials or some of the presentations that people have made available there, feel free to check it out. But for the sake of time, I think we should move on to the TASOC presentation. So Derek, if you'd like to go ahead and share your screen. All right, I'm seeing your slides.
Yes, there we go. Okay.
Okay, and I can hear you too. Great, go ahead.
All right, great. So thanks for having me here. I'm going to talk a little bit about the TASOC pipeline. As with Eleanor, I'm going to go rather quickly, and you shouldn't expect to learn everything about it from this, but I'll just try to touch some of the high points. I'm sort of representing the TADA working group within TASOC. So Rasmus and Mikkel and many, many other people who contributed to this. So this is an open source project, but by open source, it means something a little bit different perhaps than what we had just heard, in the sense that the software is completely available. It is hosted on GitHub. You can go look at it. However, rather than providing a tool like Eleanor that folks can use to produce their own light curves, we provide the light curves. And because those are numbered in the 10 to the 7+ range, this code is not well hosted on your laptop. So, I wouldn't recommend downloading it and trying to run it on your laptop, but if you're feeling really aggressive, I suppose you could try. It runs normally on a supercomputer out at Aarhus, but certainly all the aspects of it are there. You can go look at the code, you can go look at the algorithms. There are 3 papers describing it. 2 are accepted and up on archive, and the 3rd one hopefully will be soon. So it basically is broken into 3 pieces, and I'll talk quickly through the 3 different pieces, concentrating on the first 2. So the first one is the photometry module, then we move into the systematics correction module, and then we have a classification module where we try to make sense of what we're looking at, since the numbers are so large. So to start off, we do background correction, and this process I think is probably sounding pretty familiar at this point. We break the image into many little tiles, 64 by 64 pixels. We do a source extractor style background estimation in those tiles. We have a special treatment for these corner flares that we parameterize, and then we sort of map the 64 by 64 pixel and the parameterization back onto the original image through smoothing. And so you can sort of see how that works with the original image, the background, and the subtraction. The subtraction in this case is imperfect. There's still some of that corner flare there. So those pixels get flagged and carried through the rest of the way, so that if you happen to have a star that sits there, you'll know. We also do timestamp correction. The FFIs themselves contain timestamps, but of course those are based on the center of the image. And if you want to do true barycentric correction, that depends on the exact coordinates. So we rederive barycentric correction for the coordinates of all the individual targets. And depending on the level of precision that you need, that may or may not be of value to you, but typically we're talking about corrections that are in the tens of seconds range. We do aperture extraction. So we don't have fixed apertures. Instead, we have an algorithm that's based on K2P2, which was developed for the K2 mission. And that essentially does pixel clustering. So we go from the first to the second image here. We do a sort of machine learning pixel clustering algorithm. Then we do a watershed image segmentation, and that sort of defines where our apertures are. So they can be very odd shapes. The advantage of that is to allow us to work better in crowded fields. It's not PSF fitting, obviously still aperture extraction, but it, I think, is an improvement for crowded fields. We do have the ability to do PSF, but it's not implemented in the product yet. Bright stars get special handling. I was a little late coming here because I was listening to Tim White's talk. And so basically we incorporate Tim and Ben's work. So we recalculate the smear correction for bright stars. We do halophotometry for the saturated stars, and that all happens sort of automatically under the hood. So once we've produced these first order light curves, we do some systematics correction on them. So to try to take out what the instrument has helpfully put in for us. So we do that in two different ways. One is the way we've heard already, which is the co-trending basis vectors. We do calculate our own ones. We divide the CCDs into 16 CBV areas per camera per the image over there. That's sort of building in the expectation that we expect some systematics to depend on the distance to the center of the camera. And so this tries to sort of account for that so that we don't end up depending on many, many different CBVs. But otherwise, it's very like what you've seen before in terms of CBVs. We have a second approach as well that we use, and that's an ensemble-based approach. So essentially, we construct an average standard star based on nearby similar stars, so stars of similar brightness. And the focus here is on sort of characterizing and removing local systematic effects. So these two are complementary, and I'll talk about that a little bit in the next couple of minutes. But we see them as both of interest depending on the kind of target you're going to look at. And something I should say, which I think everyone else who is presenting here would agree with, is that the best thing you should do is look at as many different light curves as possible from as many different pipelines as possible, because they all do things a little bit differently. And if you really want to know what the systematic effects are like, you need to look at a bunch of them. The ensemble method tends to fail for really bright stars, and that's just because there aren't enough nearby similar stars to make a standard. If your star is fourth magnitude, there are unlikely to be lots of other fourth magnitude stars nearby in the field to construct a standard from, and so it's not going to work. Once you're above about eighth magnitude, then you'll get light curves for both, for CBV and for ensemble. So what do they look like? Well, for most stars, the results are of similar quality, although the CBV method generally outperforms the ensemble method. So here are 4 examples. The tick numbers are there, and then the parenthetical numbers are the camera, CCD, and magnitude. And on the top is the ta-da raw light curve, and then underneath are the extracted ensemble and CBV light curves laid on top of one another. You can see that they're broadly similar, but there are differences. The CBV method, for the ones shown here, tends to do a better job of removing what are probably systematics from the spacecraft. However, there are times where the ensemble method does work better, and that's typically the case where you have stars with low frequency variability, so long, slow variations, and or just spatially localized noise, whether from scattered light or issues with guidance or anything like that. So for example, if you look at the light curve on the top left, you can see that the raw light curve has some noise and some issues toward the end. The ensemble light curve handles that really nicely. The CBV light curve, let's say it doesn't. It tends to, when it fails, it tends to fail in a fairly spectacular and noticeable way, which I suppose is good. Performance measures I won't talk a whole lot about, but here is an image of showing the 1 hour root mean square noise as a function of magnitude. It looks a little complicated just because there are too many points. And so when the density gets high, we just switch over to contours instead. But the takeaway here really is that the lower envelope of the noise metrics, regardless of how you do this, follows more or less the Sullivan et al. Expectation. And the exceptions tend to be stars that are highly contaminated in very crowded fields or with very bright stars nearby. So since some people apparently still think that this is an exoplanet mission, even though we know better, I thought I'd show an exoplanet. So HAT P7, so the black on the top panel, the black dots are the raw FFI light curve from the TASOC pipeline. When we go through the CBV correction, we end up with the red ones. And for comparison, and just to show off a little bit, I didn't do anything with this except pull it out of our archive. On the bottom, I have the 120-second cadence in black and the FFI light curve laid on top of it, phased to the planetary orbit. So we're quite happy with the performance. So we do classification. I'm not going to talk about this. If you saw Jeroen's talk from this morning, then you saw all about this. If you didn't, then you should have seen his talk from this morning. But here's the takeaway diagram is just that we do classification using a variety of supervised methods feeding into a meta classifier, which is also a random forest. That gives us some top level classification. And then we have some unsupervised clustering that combines with the top level classification and some other information, not just the light curves from TESS, to try to draw some finer boundaries. And it does, I would point out, if you look on the bottom right, leave room for new classes, so things that don't fit with anything else. So there's some discovery space. So where are we at now? Well, we're running behind where we thought we'd be, because every software project always does, and COVID has not helped us any. But we do have data releases available on the TASOC site, as noted in the bottom. We've got about 12 million or so light curves there now from sectors 1 through 6. We decided then to switch to the Kepler field ones. So we've been working on 14, 15, and 26. Those will be out later this month, and then we will switch back starting at sector 7 and continuing ahead. So that's kind of where we're at right now. So roughly another 10 million or so light curves will drop later this month, if you're interested in hearing the fans on your laptop work really hard. All right, I think I'm done. I ran a little bit over, I apologize. But thank you very much, and happy to take questions.
All right, thanks very much, Derek. That's really exciting to hear about, all of these light curves, and as much as I know I shouldn't, I really want to, download, 10 million light curves onto my laptop and see what happens. But for the sake of time, I'm going to encourage you to look to the Slack channel to answer any questions that are there. But we should probably move on to the next presentation from Doug Caldwell regarding the SPOC FFI pipeline. So Doug, if you want to go ahead and share your screen.
Can you see that?
All right, that looks great. And I can hear you, but you're a little bit faint.
Okay, let me. Is that better?
That sounds better.
Maybe. Yes, no?
Yes, that sounds
Much
great.
fainter?
Can you hear me
cool.
now?
Thanks, sorry. I had crappy headphones. I'm going to talk a little bit about the tess-SPOC light curves, and I'm assuming you all know all about the tess-SPOC data product, so that makes my job here very easy. Because the whole philosophy. First, I guess I'll say I'm doing this as a representative, but there's a lot of people who did this work, and it's basically the entire SPOC and the team there. And the way we approached this generation of light curves is we realized we were already calibrating FFIs to be delivered to the mast as part of the calibrated data products, and all we needed to do was to make the calibrated FFIs look like 2-minute target pixels, and then we could just run them through the pipeline essentially as is. And of course, it never works as is, as you expect, so we had to go and do a bunch of tweaks to adjust things. But now that that's been done, it's really straightforward to run this. So the light curves, the big difference in our approach is we calibrate the FFIs for the CCD related effects, the bias and the dark and the smear, but we don't do any of the sky background on the FFIs. We first select targets out of the FFIs, and since the approach we took was to try and be as create as minimal an impact as possible to the existing SPOC pipeline. We did some tests early on and found out that we could handle something like 10,000 targets per CCD without really any problem. So that puts us at about 160,000 targets. So we set that as a limit going in, and the way we choose targets to cut out is we first pick all the 2-minute targets, which is about 20,000 per sector, and that now includes all the 20-second targets, which are also 2-minute targets. And then we go through a set of targets where we specifically look for these, and there's a couple criteria that we use. One is they're bright infrared, so HMAG less than or equal to 10, or they're nearby, so the distance less than 100 parsecs. This is all using the TIC parameters. We just to limit the effects of very crowded fields, we apply a crowding metric cut to these they have to be greater than 0.5, so meaning at least 50% of the flux in their optimal aperture comes from the target based on our model images we create, just like with the 2-minute data. And then we're limited to test mag less than 16, primarily because the way we had handled running the pipeline, we only pull out targets in general at down to 16 for the pipeline analysis. So to go deeper just made it more complicated. So that was easier to just limit there. And that selects usually a few tens of thousands of targets across the field. And then the rest of the target budget, we just fill with field stars with a magnitude cut of 13.5. And we usually don't get there. We usually get close on some CCDs. A log G greater than 3.5, just to sort of arbitrarily choose non-giants, and a crowding metric greater than 0.8. So we're a little more stringent here. So basically 80% of the flux has to be in their aperture. And again, it's the target selection is done on a CCD by CCD basis. So you can see in the fields that go through the Milky Way, we often won't reach the full 10,000 targets per CCD because we run out of uncrowded targets before we hit, when we hit the 13.5 magnitude limit. The data products are available at MAST through the high-level science products. They're the same data products as are available for 2-minute data, except at the FFI. So that they're target pixel files, which include the pixels, the calibrated pixels, the aperture definition for the optimal aperture, and the background correction for each target. And their light curves, which include the simple aperture photometry, PDC-SAP, all the data quality flags that are available for the FFI processing, which is a subset of the full set. Is that true? Now that I said that, I'll have to think about that if that's true, actually. And I'll post my answer. And then we also include, I think one of the things that'll be helpful is we include the full set of co-trending basis vectors that are computed at the 30-minute FFI cadence from the targets at 30 minutes. So this includes the single scale basis vectors, the spike basis vectors, and the multi-scale 3-band basis vectors. And starting with sector 36, which we're going through in the process of delivering now, we're now running TPS. We had been running the transiting planet search in the mode where it just computes the precision, the CDPP for the targets. And we realized that we could do without, again, very much impact, do an actual transit search on these 160,000 targets and run DV on the results. And so we started doing that, and we're going to be delivering the data validation, the DV products, which will include the summary report, the mini report, the full DV report, and then the XML file with all the results for the DV search for each of these sectors. And that's going to start with sector 36. We aren't going to go back and retroactively do the sectors we've already delivered, I think was the decision, just because that's more of an impact and more of a pain. And so those should be available soon. The data that we've got posted so far, year 2 is there in full. Year 3 is there, and I'm doing this in a weird order, you'll see why in a second. Year 3 is there up through sector 34, and 35 through 39 are in the process of being delivered and or ingested at the MAST. We went back and reprocessed, as part of our reprocessing of the year 1 data at 2 minutes with the updated SPOC pipeline. We started processing the FFI targets. And so we've processed all of them. We've delivered 1 through 7, which are up at the MAST, and 8 through 13 are delivered and being ingested. And so 9 through 13 will be up soon, I think sort of 2 weeks-ish. Sector 8, there were some issues with PDC that we're trying to figure out if it's an easy fix, and if so, we'll probably reprocess that and redeliver it. We ended up getting some noisy results on a couple of the CCDs that were surprising because they were different from what we saw in the target 2-minute data. And the nice thing about this is since we're basically running the same pipeline, the results usually mirror pretty well the 2-minute data. So if we see issues at 2 minutes, we'll probably see the same thing here, and we already know what to do about it or have already fixed it. So those should be up soon. And finally, I went through, as everyone said, I think the key here is we've got a lot of different approaches to generating all these light curves. Some are certainly better than others. We don't have as large a number as many of the groups but I think we've got a set of products that are well known and well understood by the community. So that's helpful. And just a couple of the distributions of the kinds of targets, the three sets of selection that we use. You can see in the magnitude distribution in the bottom left, the dark blue is the 2-minute targets, and those range out to faint targets, whatever was selected. The cyan are the ones that we specifically include, so they tend to be either bright because they're bright at HMAG, or they're close by, so there's some faint, small faint stars that go out to about 16th mag. And then the red are just the magnitude limited ones that we fill up the target list with, and you can see the different distributions. You can see on the right the cut with distance and brightness there, and how the targets lay out here. And finally, for comparison with QLP, which is looking at similar things, I just looked at these last night for 2 sectors. I sort of chose somewhat at random, 20 and 21. The overlap of our targets is very significant, not surprisingly, because we have pretty similar selection criteria, and QLP is going generally fainter. I think they're going to 13th mag everywhere, and we're not reaching that usually. But there's a lot of overlap, and I want to look now and see what are these sort of 4,000 odd targets that we have that they don't have, if there's something weird about them, in magnitude space, or what makes us pick them and not QLP. And I think that's about it. So we have light curves available at the mast. The data products are the same as are available for 2 minutes. And I guess the only other thing to say is we're also wondering what's going to happen with the new shorter cadence FFIs, and that'll be an increased processing load, and we'll have to see how that impacts things and makes things complicated or not. And that's it.
All right, great. Thanks very much, Doug. I think, well, I'm gonna take the organizers, preference and just ask one quick question, which is, what's sort of the limiting factor for making more light curves with SPOC? Do you guys just, or do you have an idea of which light curves you want to process next? Do you want to go back and do some of the ones that were fainter, or just move ahead with the newest batch of data?
Because of the way we're set up, we essentially, it's easiest to do this in parallel with the 2-minute data. So when we get a new sector from downloaded, it's ingested into the database, and everything's available. We run the pipeline, and then when the next new sector comes in, we sort of shift the stuff from the previous sector offline immediately and start on the next one. So it's easiest to get the FFI processing done in parallel or just after we do the 2-minute data. So going back and reprocessing, we should redo sector 13 is much more of a pain, because we have to reload all the old original raw data products and start over. And so there's no plans currently to do any major reprocessing to add more targets. If we do make changes, it'll basically be going forward, with new sectors as we go on.
Cool. All right. Well, thanks very much for that info, and look on the Slack to see if there are any more questions regarding that pipeline. But yeah, thanks again to all 4 of the speakers on all the FFI pipelines today. I really appreciate it. So now we're just going to turn the recording off for this session, and basically allow for a quick some 1-minute lightning presentations. So I'm gonna go look on the Slack and start with the first one I saw, which is from Christina Hedges. So Christina, if you'd like to go ahead and give us maybe a 1 or 2 minute presentation on tess-backdrop.
Okay, I'll try and be quick, so I'm keeping it time. Can everyone see my screen? Cool. So
yeah.
I just wanted to show you guys tess-backdrop. We've heard some really cool and awesome pipelines that do really cool and awesome things and get you guys to the light curves. And this is not that tool. tess-backdrop is a tool to take FFI data and create a model just for the scattered light background and the jitter noise in TESS, and then create that model in a way that is very, very lightweight so that you can apply it almost instantly. The idea is that it's a simple linear model, and so the data, if anyone can see, if I zoom in, the data is here. I can't zoom in while I'm sharing. And then we create a model that looks a bit like this, and then you get beautiful data minus model. There's some information on the GitHub pages about this tool. It is under development, and so right now, if you want to use it, I would get in touch with me on Slack or open an issue because I'm in the middle of developing this. I'll show you the idea behind it, which is that if you were using Lightcurve or however you're getting FITS files, the idea is that you will be able to do something like this, which is that you have some sort of TPF, be it a cutout of the FFIs, or even potentially a regular TPF. And then you would just pass it to this backdrop object, and then it'll correct it in milliseconds. And it'll look something like this when you, instead of this wiggly light curve, it'll look something like this. More than that, the idea is that it will be able to correct TPFs and light curves for you, both for the scattered light and the jitter, so that you can create corrected light curves that look a little bit like this one at the bottom. So these are the regular light curves. And then if you use the background corrector, you can get light curves that look like the black line here. And for this campaign, and this was an early campaign with a lot of jitter noise, you can improve the CBPP, you can improve the precision of this light curve pretty significantly. So the idea is that tess-backdrop is creating these coefficients for you, and you can apply them in milliseconds and get corrected, systematics removed TPFs. And there are ways to apply in the light curves. Like I said, this is under development. And so right now, this will work if you want to use a particular sector, because I'm still generating a lot of the files that make tess-backdrop work and make it work really fast. But having users is really great. So if anyone wants to talk about more about this, about the techniques that are involved, let me know. Open an issue on the GitHub. You can find us if you go to our SS Data Lab GitHub and go to tess-backdrop. You should be able to find it.
Great. Thanks very much, Christina. All right, next up, I see Michelle Kunimoto has requested to talk a little bit more about her tool. So Michelle, if you'd like to go and share that.
Okay. So yeah, this is just a quick 1-minute slide I've got here. For those of you who are interested in planet candidate vetting, let's say you found a promising signal, or there's even an old TOI that you want to do a follow-up work on. Identifying nearby and background eclipsing binary false positives is really important for that kind of analysis. And these are some of the most common types of false positives from Kepler data, from test data. Basically, if you've got your aperture that might be several pixels wide, and it could have blended light from a contaminant in that light curve. So you want to make sure that your transit source is actually the on target star and not a different star. So this is actually work that has been primarily done by Steve Bryson from NASA Ames. Those of you who've been around since the Kepler days may recognize him. He's done a ton of work on identifying these kinds of false positives with Kepler data, and he's now turned his attention to test data. So I've been working with him on this tool. Right now it's hosted on my GitHub. Those of you who have any questions about it, feel free to send me a message on Slack. It's also in development. I've posted a tutorial in a Jupyter notebook with the workshop, if any of you feel brave enough to download it and try it out yourself over the next hour. But yeah, just wanted to let people know that this was a tool available, and I hope it is useful for you.